Welcome to the Lipid Maps Podcast. My name is Matthew Conroy, and today we're joined by Adriaan Minnaard, who's chair of the Chemical Biology Department at the University of Groningen. Adriaan, it's great to meet you and to talk to you finally.
Thank you, Matthew. Very happy.
Now, as well as being chair of the department, your group focuses on the organic synthesis of complex molecules. Some of those are the sacrolipids in Mycobacterium tuberculosis in the membrane. Can you tell us something about those lipids and their role and their importance to us?
So, as you know, Mycobacterium tuberculosis is the cause of TB, the cause of tuberculosis, a highly infectious bacterial disease. And the bacterium is able to survive in the human body for many years. That makes the disease also so difficult to diagnose and to treat. And it turns out the bacterium has a very complex outer membrane consisting of numerous lipids, many of them we don't know the precise structure yet. And these lipids are there for a kind of physical barrier. So the bacterium is basically guarded by this outer membrane, but also that these lipids have an important role in the immune system. So some lipids activate the immune system. So the body has learned when it detects these lipids that TB is there, but others, they actually attenuate the immune response. So it's a complex mixture of effects. And that's why people are interested in the structure of these lipids, but also having them available to study them one by one. And that's very complex because if you isolate them from the bacterium, which is anyway difficult, right? Because you're dealing with highly pathogenic bacterium, but it's also very difficult to get these compounds pure.
Yes. So many of them they're fatty acids, as you said, but they're attached to sugars as well. There's a whole group of them, one of which is called, a whole family are called, are they called DATs or DATs?
We call them DATs.
DATs, okay. And there's a family of them, and one in particular, DAT2, which is trihalose esterified with two acyl groups. You found something very unexpected when you synthesized that molecule. How did you spot it, and what were your initial thoughts on that?
So we noticed in the literature that these dots, and there are three main components of them, they were always isolated from the bacterium as a mixture. So they were not separated because that was very difficult. The only difference is in the stereochemistry, or in the fine structure of the fatty acid. So they all three contain trehalose, and the esterification place on the trehalose is the same. It's just the fine structure of the fatty acid. So they were always isolated as a mixture, and this mixture is known to be active again in the immune system. So they bind to the mingle receptor in particular. So we set out to make all those three compounds separately because we wanted to know, is there now one of the three very active, or are they all three kind of the same activity? And for the DOT1 and the DOT3, that worked fine, and they were compared to the natural extract, which is then a mixture, of course. They were spot on the LCMS, so they had the same retention time, and they had exactly the same mass spec and the mass fragmentation compared to the natural material. But surprisingly, the DOT2 had exactly the same mass spec, but the retention time on LC was off, and it was not a bit off, it was clearly off. And that is strange because you would expect, well, it must be trehalose, it must be fatty acids, the mass must be the same, the position of the esterification must be the same, otherwise you would see a difference in the mass spec. So the only difference could be the stereochemistry of the hydroxy group and methyl groups in the fatty acid. But if that's the case, why is the difference on HPLC retention time so big? Because it was 1.5 minutes on a retention time of 8 minutes. So it was really way off. So that surprised us a lot.
That too, reading your paper has always been enigmatic because it was initially thought to be a sulfate, and actually there's no sulfur in it at all. So that's a fairly major misidentification.
Exactly. Yeah. I have to give credit to the earlier researchers because this fatty acid, and in particular, so not so much esterified to the trehalose, but the fatty acids called mycolipinolic acid, has been found first in 1968 by Polgar. And Polgar is a very important, very famous tuberculosis researcher on lipid, and he reported this compound in 1968. So that's way back. So little NMR, infrared chromatography. And he said, well, this fatty acid has certain stereochemistry, and out of the 4 centers, I can deduce 2 of them. That's pretty certain. And then the other ones, I'm not certain. But he calls for those 2 centers, they probably have an erythro relationship. And that's what he said about this. And indeed, then a couple of years later, let's say 10 years later, people found, but the fatty acid is there, but it's esterified to trehalose. And then some people thought, but there is a sulfate on. I never understood why that mistake was made, because then you have a completely different structure. But then in the end, they said, no, it's esterified to trehalose. And there it becomes very misty, because then some people ignored the statement of Polgar that the stereochemistry he wasn't certain of. And one paper, understandably maybe, but they misinterpreted the statement erythro, and they basically said, then it has to be syn, in what we call it now, syn relationship, but erythro translates into anti.
And he hadn't said that definitively anyway.
No. So from that on, everybody was confused. So that was not certain. And as the compound is pretty omnipresent in TB bacteria, the compound was actually isolated many times, and also sometimes stereoisomers were made, but the whole picture wasn't clear, and many people were wrong. Yeah.
So having found the completely erroneous retention time of the molecule you had synthesized versus the natural product, and we should say mycolipinolic acid is an unsaturated fatty acid, isn't it? Variable length, sort of C24 to C28.
Yeah, that's very common in tuberculosis bacteria, makes also the identification often difficult. All these lipids come as homologs, as we call them. So they all have a number of chain length.
And it's methyl branched at carbons 2, 4, and 6 with a hydroxy at 3. And 4 and 6, the stereochemistry is not in doubt. It's the 2 methyl and the 3 hydroxy that was initially said it may be erythro, which is not syn, but it was in doubt. You determined the correct stereochemistry, but to do that, you had to synthesize all 4 possible stereoisomers. And most of our audience are not synthetic chemists. Can you just give us an idea of how challenging that is? The little synthetic chemistry I know that synthesizing stereo-specific molecules is difficult.
It was challenging. For us, it was also challenging from a synthesis point of view, in the way that we thought, okay, there are many stereoselective methods out there to introduce hydroxy groups and to introduce methyl groups. But what now if you have to make them all 4? Because that forces you in studying the methods and look which stereoisomers are readily prepared and which stereoisomers are difficult to prepare. And that was for us really instructive, because some isomers, 2 of them to 4, were readily prepared, actually. So there's just methodology there that you can follow. And the other ones were actually not easy to prepare. And for one, we even had to use another synthesis strategy. And so from a synthesis point of view, apart from the lipids, the interest in lipids, it's for a synthetic chemist, of course, interesting to see, with all these papers on stereoselective synthesis, do we cover the whole field? Or are there still stereochemical arrangements that are less easily accessible, but turned out to be the case? So in that sense, it was laborious, also very instructive, as I said. And another point was, and that was a surprise for us, is that we had made 1.2 isomer, the wrong one, apparently, because it had a different retention time. And there, in that synthesis, the esterification of mycolipinolic acid to the trehalose was actually pretty straightforward. So the yield was okay. It was a normal esterification reaction, nothing special. But the other 3 were actually very, very complex. So the normal esterification methods didn't work, whereas the only difference is stereochemistry of the fatty acid. So that was surprising for us. And so we also spent quite some time in selecting sometimes very peculiar esterification reactions in order to get the product.
So finally, you made all 4 and presumably compared their retention times and their NMR spectra with the natural product, and definitively proved which one was the natural product. And it's curious that just a stereochemical difference like that causes such a high retention time difference. Do you have any hypothesis why that might be?
that surprised us as well. Well, to start with, and that was a nice finding in a way, is that if you look now at the 4 stereoisomers and you look at the proton NMR spectra, you basically have to conclude you can't discriminate if you have only one. And so looking back, we must conclude that no one would have been able, based on only the natural material, to say this is stereochemistry. So you really need all 4 of them look at the differences and then say, it's this one. And we did NMR, proton NMR, we did HPLC, and we did gas chromatography on the methyl esters of the fatty acids, and it all gave the same answer. Regarding this difference in retention time, our best explanation is that due to the different stereochemistry in the fatty acid chain, the fatty acid chain has also a fully different conformation. So it folds different. So that means that the entire molecule actually get a different shape. And if that's the case, then you can expect a different retention time on HPLC as well.
That would have been my guess as well, that somehow the stereochemistry means it folds up differently. Maybe there's a hydrogen bond to the sugar that's accessible in one and not the other, something like that. So it's great that it's finally been determined, and it's meant we've corrected the stereochemistry of many of these molecules in the lipid maps database. We went through and fixed them all, so they've been corrected too. But it does raise the question, an interesting question, of how many more things might there be out there in the literature where either the original analysis was wrong or the original analysis has been misinterpreted, where someone said it might be this, but we're not sure. And then down the line, other people have said, he said it was that, look. Yeah, and it's an error that's perpetuated.
But worrying, isn't it? So as such, I mean, the phenomenon that upon chemical synthesis, the structure of a natural product has to be corrected, that's a rather common phenomenon. It's not, I don't think it's because people are sloppy or so. Indeed, misinterpretation is often the case, but it's also, of course, very complex from, in particular, lipids with these linear structure to do your structural analysis right. And the nuance of, well, I think it's this one, but I'm not entirely sure, is indeed often a bit neglected in subsequent papers where an author says, no, what is it? Okay, he says it's that one, so that's what I draw. And another point is what I often see is that, of course, if you go more to the biological sciences, mass spec is a very dominant analysis technique, probably rightly so, because it is very informative, but not when it comes to stereochemistry.
No, absolutely.
And that is then a bit sometimes overestimated, or people say, but it has the same mass spec, so it has the same structure. No, for stereochemistry, you can't say that. So I think, but look, now I'm talking as a synthetic chemist, is that if you want to use a lipid, glycolipid or whatever, for biological studies, then you have to, of course, you can do a lot of biological studies having the wrong structure, but you don't know. I mean, that as long as everyone uses the same structure, you can, as long as you don't go to the molecular details, you're probably pretty fine. On the other hand, if you want to apply these molecules like we like to do, we like to apply these dot molecules, for example, in an ELISA. Because if you find these molecules in blood or sputum of a person, then you're sure the person has TB, because these compounds only occur in Mycobacterium tuberculosis. That means that you need the pure molecule, and then you need to have the structure right, because you don't fool enzymes, or you don't fool receptors, right? They will bind only with that affinity to the correct structure.
And and as you showed, it was a real effort to synthesize specifically the stereochemical forms of the molecule. TB does this relatively effortlessly all of the time. By enzymes, it's not a problem at all.
No, it isn't.
And it's important to have the right one, because as you showed, the natural one is far more effective in activating the immune system than the incorrect stereocenters.
That's right. And it also showed us is that when we looked in literature to the efforts people made to use these dot molecules in an ELISA, there are around 24 papers out there that say we do have an ELISA that is good for measuring or monitoring dots, but they always use the mixture. And all 24 of these papers, it becomes clear that people can't reproduce those ELISAs. And there is even a kind of a meta paper, a kind of review who says, well, we compared all of those and it's very difficult to get them reproducible. And here you have our ELISA and that's much better. And then the next group say, yeah, but also it doesn't work in our hands. And what we conclude basically here is, yeah, but that's maybe not so strange because these DOT molecules, they come as a mixture. And what we see in clinical samples of patients is that these levels of DOT1, DOT2, and DOT3, they vary tremendously from one patient to another one. So it's not so strange that you get mixed results when you try to use this mixture on an ELISA. You would like to have an ELISA on one particular compound.
Well, it's great that it's been corrected, and it's been really nice to talk to you. For our listeners, if you'd like to read Adriaan's paper, it was published in Angewandte Chemie earlier this year, and the title is Asymmetric Total Synthesis and Structural Revision of DAT2, an antigenic glycolipid from Mycobacterium tuberculosis. Adriaan, many thanks for taking the time to join us on the podcast today, and thanks to everyone for listening. We hope you'll join us again for another Lipid Maps podcast soon.